An embedded real-time multi-threaded solution for HVAC control units by Matthew Dietrich. Most HVAC systems in our houses today contain an electronic controller that makes the system overall more efficient and intelligent. HVAC equipment uses an embedded controller system to control the operation of a heating and/or air conditioning system. A sensing device is used to relate the real temperature with a desired temperature. The control systems typically have analog and digital inputs that allow inputs of temperature or humidity from sensors and analog and digital outputs for control of the HVAC equipment. HVAC control systems can be classified as soft real-time systems. Soft real-time systems are any system where the operation is tarnished when outcomes are not produced according to the identified timing constraint. The development of commercially available sensors and software in the past decade has led to a rapid progression of the HVAC control module industry. And here we can see the sensors and the human interacting with a control application and outputting to actuators and data storage. To implement the solution, a waterfall-based approach was used where each phase must be completed before beginning the next phase. The waterfall model accentuates that a rational evolution of phases must be taken throughout the software development lifecycle. The waterfall module is a sequential design process in which progress is seen as flowing steadily downwards like a waterfall throughout the phases of conception, initiation, analysis, design, construction, testing, deployment, and maintenance. The advantage of waterfall development is that it allows for departmentalization and control. A schedule can be set with deadlines for each stage of development, and a product can proceed through the development process model phases one by one. The waterfall model is not a good model for complex and object-oriented projects and is not suitable for the projects where requirements are at a moderate to high risk of changing, because it does not support iteration and new features cannot be added once the requirements and design phases have completed. And here we can see that in my work, the requirements and analysis phase was equal to acquiring and research hardware components and programming methodologies. The design phase was implementing hardware circuitry. The coding phase was implementing the programming control logic, and testing was actually testing and documenting the system. The hardware microcontroller is Arduino is a well-known platform based on user-friendly hardware and software. Arduino boards are able to read inputs such as from a sensor or button and turn it into an output like turning a motor on or turning an LED on. The Arduino Uno contains a total of 14 digital input-output pins, and 6 of those can be used for pulse width modulation. 6 analog inputs, and a 16 megahertz clock, and it uses a USB connection to program the device. It contains an Atmega 328 processor that comes with a number of features like timers, counters, interrupts, and pulse width modulation. The Atmega 328 is an 8-bit controller and comes with 2 kilobytes of SRAM, 32 kilobytes of flash memory, and 1 kilobyte of EEPROM. And it uses the Arduino IDE to program the Arduino board. Sensors are mechanisms used to yield signals to measure physical parameters and detect events. A shortcoming in control technology is that most homes have only one sensor per HVAC system. This sensor is typically in the thermostat, which is usually centrally located in a home and therefore does not capture the temperature variations throughout the home. A DHT11 sensor is a digital temperature and humidity sensor that contains a humidity sensor and thermistor in order to measure the environment conditions and output a digital signal on the data output pin. It has the ability to measure temperature in the range of 0 to 50 degrees Celsius and humidity from 20 to 90%. at an accuracy of plus or minus 1 degree Celsius and plus or minus 1% for humidity. Infrared detectors are microchips that contain a photocell tuned to listen to infrared light and are almost always used for remote control signal detection. The remote control contains a matching IR LED that emits IR pulses that are read and decoded by the IR detector. Actuators are the interface between the control system and the mechanical system and are crucial to accuracy. Software receives data from sensors, performs necessary computations, and sends a signal to external sources. A liquid crystal display is a monitor unit built using liquid crystal technology. In an embedded system context, LCDs are a device to display system state data and fault messages to the user. The LCD display needs 6 Arduino pins configured as digital outputs as well as a power and ground connection. A DC motor is the most common type of motor used in electronic systems. It's one of the best and most cost-efficient ways to control the DC motor is to connect the L23D motor driver integrated circuit with the microcontroller and the motor. The integrated circuit is capable of manipulating both speed and spinning direction of 1 or 2 DC motors. Speed of a DC motor is controlled by varying its input voltage. A common technique for controlling the speed of the motor is with pulse width modulation. PWM is a method for varying the input voltage by controlling a series of binary pulses. Here we have the demo of the hardware.
Hardware for the embedded real-time HVAC control unit using the breadboard components. We have the Arduino microcontroller, the LCD monitor to display system state to the user, a DHT11 temperature and humidity sensor, an IR detector, an IR remote, a L293D motor control integrated circuit, and a DC motor that simulates the AC system. You see the system is currently in the power off state, so nothing is displayed. You can press the power on button on the remote, and the unit turns on. It will display the current set temperature, which is currently 85 degrees and can be controlled by the remote. And the current temperature in the room is 86.5 degrees with a 48% humidity. And since the set temperature is lower than the room temperature, we have the motor powered on, you see here. And if we turn the set temperature to be higher than the room temperature, the motor is no longer active. If it goes below, it becomes active.
The software, use C++ to program it, and C++ is a good choice for embedded system development because the language contains features that permit the programmer access and control of hardware directly without forfeiting the benefits of a high-level language. C++ programs are known to be highly stable and lends itself well to systems that will be in production for long periods of time. Multi-threading is a system feature that allows your computer to run 2 or more programs concurrently. The proposed solution contains 4 separate threads that operate at different frequencies. The thread to control the remote runs continuously whether or not the system is powered on, while the other 3 threads only run once the user powers on the system. And here we can see the timing of the threads. The thread to display sensor data on the LCD runs at 1 Hz. The thread to update the set temperature and display it on the LCD runs at 2 Hz or 2 times per second. The motor control and the logic to check whether the motor should be on or off runs at 2 Hz. And the thread to get input from the remote or the IR detector runs at 5 Hz. Over here we can see the code to set the threads up. For instance, here we're gonna run the thread to display the temperature and humidity at every 100 microseconds, and the motor control thread every 500 microseconds, and thread to get the remote input at every 200 microseconds, which is equal to 5 megahertz. And here we can see the loop that the Arduino runs to continuously. This would be it. It's going to continuously get remote input at 5 times per second. Then if the system is powered on from the remote, it will start running these other 3 threads at their desired times. Here we can see the flow diagram for the system. You can kind of follow through it to see how the system operates. Arduino does not support isolated parallel threads, but has the ability to make the main loop switch its execution tentatively and thus mimic threading. The Arduino thread library allows the programmer to schedule and manage tasks, set the time between task executions, organize the code to put all sensor readings in a thread, keeping the main loop clean, and run background tasks using timer interrupts. The software begins by continuously running a foreground thread to check the power state of the system while waiting for the user to turn the system to the power on state. A background process will then run every 200 microseconds when the power is on to listen to other user input from the remote control to change the system temperature. And we could use McCabe's metric to calculate the complexity of the system. So we have 20 edges minus 21 nodes plus 2 times 4 tasks gives us a complexity score of 7. Therefore, we can be fairly sure this module is reliable. The state-of-the-art HVAC technology. Intelligent thermostat systems can reduce the energy consumption of HVAC units by scheduling the HVAC operations dynamically based on data of past usage patterns. Programmable thermostats have the ability to change temperatures set point based on a predefined user input schedule. Smart thermostats are a new technology in connected thermostats that contain computation features and thus are capable of supporting advanced software tools to monitor system performance, detect faults, and ensure proper operation. Smart thermostats are currently the state-of-the-art application of temperature set point control. Several HVAC zones can be created and controlled independent of each other by using additional actuation sensors and hardware at multiple locations. Modern advanced occupancy sensors have the potential to measure the number of people and their activity level in homes and monitor and control the system accordingly. Modern state-of-the-art HVAC systems deploy machine learning algorithms to predict occupancy and temperature set point patterns to increase system efficiency and energy savings.